Hey everyone. So we're going to wrap up section 4 of chapter 4 by talking about the second fundamental theorem of calculus. I just want to say beforehand that if you go to look up more information about either of the fundamental theorems, there's no reason one is called the first and the other is called the second. So depending on what source you go to, those numbers, the first and second, could be switched around, but the two theorems are both called the fundamental theorem. So there may be some confusion if you use other sources, which I encourage you to. You should use other sources, just don't let that trip you up. Alright, so far we've had definite integrals be a number. So if we had some definite integral from a to b of some function f of x, we would get a number out of that, right? You can construct integrals in such a way that you get a function out, and that's what the second fundamental theorem of calculus tells us about. So, we could have a function capital F of x that is defined by the definite integral from a to x of some function. Now I'm going to use t's in here, and the reason we use t's inside of this integral is just so we don't get confused with the x's that are here and the variables that are here, and so we usually call these t's dummy variables. So we're really going to have everything be in x's at the end of the day, but we use t's here just to not be confused. So these are called dummy variables. You may see something about that. So this integral gives us a function, and we usually call that the accumulation function because it is a function that tells us how much area is accumulated. Let me put area accumulated from let me just say this, from a to x. So whatever your starting point is, this function will tell you how much area you've gained for any number x that you want to plug in. Because remember, the integral is just a operation that sums up little tiny pieces of area up to a point that you tell it to stop. So that's what the second fundamental theorem of calculus deals with, is this kind of thing that we get. If we go from a to x, we get a function of x out. And then there's also another trick we're going to do with that here in a minute, but let's just look at this accumulation function for a second. Alright, so if we have this function of t, let's find capital F of x. So capital F of x. Now if they don't tell you where to start, like what this a is, we usually just put a 0. And for a lot of the uses that we're going to have for this number doesn't matter at all. And I'll show you why later in this lesson. So we're going to go t cubed plus t dt. Alright, so if we evaluate this, we get t to the 4th over 4 plus t squared over 2 from 0 to x. Now these are nice to evaluate, because since you're just plugging in a variable, there's not going to be any messy numbers to deal with. Oops, sorry. That's going to be an x squared over 2. Alright, so this here is capital F of x. This tells us how much area we accumulate to up to a point. And we're going to evaluate f of 1 and f of 2. So f of 1, we just plug in 1 for each of these x's, so that's going to be 3/4. And then f of 2, plug in 2, so that's going to be 16 over 4 is 4, plus 2 is 6. Alright. So that's all we did there. We came up with the accumulation function, and then we plugged in these numbers. So the area accumulated up to 1 is 3/4. The area accumulated from 0 to 2 is 6. Easy enough. Okay, so here's what the second fundamental theorem of calculus really deals with, is taking the derivatives of these accumulation functions. So we're sort of taking the derivative of an integral. And this is going to be a concrete example of how that works, and then we'll look at it a little more abstractly. So if I wanted to find this function, I would do the same thing I did before. This would be t squared over 2 plus 4t, evaluated from 0 to x, so that's x squared over 2 plus 4x. And then it asks us to find the derivative. Again, just in case you were wondering, I'm ignoring this 0 because plugging in 0 there just gets me 0. So I'm not ignoring it, it just goes away. All right, so we're going to take the derivative of that. So derivative of x squared over 2 is x. Derivative of 4x is 4. And here's what you should notice. That derivative is the same as the function that was right here, except now it's in terms of x. It's in terms of the upper limit of integration there. And so that's what the second fundamental theorem of calculus really tells us about. Find the derivative of fx. Oh. Okay. So it is saying if you have, let me start by writing this again in general terms. So again, this is our general term for the accumulation function. If you were to take the derivative of both sides of that, and I should have left myself more space to do that, but I didn't. So if we're going to take the derivative of both sides of that with respect to x, we get little f of x. Maybe I'll just put an equal sign right here. So as long as you're going from a constant to just regular old x, you get back out this function, but in terms of x. Now that's not quite the whole story. And let me just preface what the whole story is right here. If you're going to something more complicated, so let's say we're taking the derivative if this upper bound is something more complicated, like x squared, for say, but let's just say it's u, so u is going to be a function of x. What we get out is little f of x again, times the derivative of u. So again, like if u was x squared, this would be 2x. We'll do some examples to see where that comes from, but that's generally what you need to know, is that if that's a function of x for the upper bound, you need to take the derivative of that. And it's the same thing here, it's just that that derivative is 1, so that's why we don't do anything with it there. Okay. So let's look at this. Have the upper bound be more complicated here. Yes, I remember why. Okay. I'm going to change this to be a 1. Not because it doesn't work if it's a 2, but because the integral is much more difficult to evaluate, and I want to do this concretely. So let's evaluate this integral and then see what's going on with these bounds. So the integral of cosine is sine. So this is sine t. And notice here I made this not 0, so we can see what happens with that too. We're going to go from x squared to pi over 2. So this is sine of x squared minus sine of pi over 2, which is 1. And that is, again, f of x. All right, so now we're going to find the derivative of that, f prime of x. So the derivative of sine x squared is cosine x squared times the derivative of the inside. So that's the chain rule, and then minus derivative of 1 is 0. So that's why this constant term always goes away, because when you take this derivative, it goes to 0. So that's why we end up with this thing just equaling f of x times u prime. Okay, so notice here we ended up with cosine x squared times 2x. So that's the same thing that was here, except we had to multiply by the derivative of that x squared. So again, generally speaking, you just take this upper bound and plug it in for your dummy variable, and then you need to multiply by whatever the derivative of that is if it's complicated like this, or if it's not just x. I keep saying complicated, but complicated just means it's not just x. All right, I don't think we need to do anything else there. Okay, the lower bound does not have to be a constant, but the way that we evaluate this situation to see what happens is we are going to rewrite this using the properties of integrals so that it is a constant. So we're going to take the integral from negative x to 0 of 4t plus 1, and then from 0 to x 4t plus 1. Oops, I didn't mean to put equals there, I meant to put plus. So now we have two integrals with constants. Now it really is easiest to do this if your lower bound is a constant. So I'm going to use another property of integrals to flip the bounds. So this is negative integral from 0 to negative x 4t plus 1 dt plus the integral from 0 to x 4t plus 1 dt. And then we can evaluate each of those. So that's going to be, are we evaluating the, we wanted to find f prime of x, right? I forgot to write it in the original problem, but we are solving for f prime of x here. So this is f of x. So what we're going to do is just plug in x for t. So I have negative 4 times negative x plus 1. Now here, since this is not just x, I need to multiply by the derivative of negative x. So I'm going to do times negative 1. And then plus 4x plus 1. And let's squeeze this up a little bit if I can. So this negative 1 and this negative sign can just cancel each other out. So what I have is negative 4x plus 1 plus 4x plus 1, and this just comes out to 2. All right. So this one's kind of interesting that the answer is 2, because that means no matter what you pick for x, if you are being symmetric here, the area accumulated is always, oh no, I'm sorry, this isn't, we took the derivative, never mind, ignore that part. Yes, the derivative of f prime of x here is just a constant. Okay. Let's go ahead and skip to here. So we're going to try to do some of this accumulation stuff visually. So I have, this is a function here, this is f of x. My accumulation function tells me about the area from 0 to x. So how much area I accumulate going from 0 to x. And then f of x is defined as the derivative of that. So again, this is little f of x. Big F of x is the area from 0 to some number. And I have a bunch of questions, so we'll flip back and forth between the questions in this picture. All right, so evaluate f of 0. So f of 0 is how much area do you accumulate from 0 to 0. And hopefully you know right away that that's none. All right, 0. All right, what about f of 7? So that means how much area do we accumulate going from 0 to 7? Well, these numbers here, by the way, are the area for each of these parts. So from 0 to 7, that is 10. All right, the next question was from 0 to 9. So we have 10 and then 2, but the 2 is underneath, so that's going to be negative 2. So that's going to be 8. All right, so far so good. What about to 12? So if we go from 0 to 12, 10 minus 2 is 8, plus 6 is 14. Okay, the next one's a little bit tricky, just because of how the accumulation functions work. So this is -5. So I'm going to sort of write this one out a little bit more. So how much area is accumulated from 0 to -5? For f of t dt. Now what's weird about this is when these bounds are flipped, so the bigger number is first, it doesn't make a lot of sense to think about. I mean, you can think about it, but I don't know, it's easier to have it go from -5 to 0 and slap a negative sign on there. So the area from -5 to 0 is -4 because it's below the graph, but then we have this negative sign out front, so this is -4. So that is +4 is the area accumulated. So this is kind of a strange property of these accumulation functions that maybe doesn't work the way your intuition says it should. If you start at 0 and accumulate area backwards, or I guess to the left, the signs flip. So the area beneath the curve here is positive as we accumulate going this way. You can process it either way, the way that I just showed sort of symbolically with flipping the bounds, or just knowing that as you move from right to left, the signs flip. However you want to process that is fine, but you need to know that that's what's going on. So the area there, the area we accumulate going from 0 to -5 is +4. Okay, this next one's a little bit tricky. Remember, we don't have the graph of f of t, we have the graph of f of x, which is defined in terms of the derivative of big F of x. So what we're going to have to do is rewrite this in terms of integrals that we're allowed to evaluate. So what I'm going to do is break this into -5 to 0 plus 0 to 7. And then I'm going to switch the bounds on this first one to be 0 to -5. And then throw a negative sign on front. Because that's how f of x is defined, is from 0 to x, f of t. And so that's what we have the information to evaluate. So this first part we just did right here, sort of. So instead of 4, it'll be -4 because of this negative sign out front. So this is going to be -4. And then this part here will be, this will evaluate to 10. Just because that's 10. So we should be getting, this is 6. All right, these questions are really good. Where is little f of x increasing? So that would be where f prime of x is greater than 0. So that's going to be where f double prime of x is greater than 0. Because remember, big F of x, sorry, the derivative of big F of x is little f of x. So the second derivative of big F is the first derivative of little f. However, we have the graph of little f, right? So we're just going to look for where the slope of little f is positive. And so that is from 0 to 4. I'm sorry, that's from -3 to 4, and from 8 to 12. I don't think I'm going to have time to write all this down, so we'll have to do this verbally. Where is big F increasing? So big F is increasing where f of x is greater than 0, since the derivative of big F is little f. So that is from 0 to 7 and from 9 to 12. It's just where that graph is above the x-axis. Where's the absolute maximum of f of x? So this is saying where is the maximum area accumulated. Remember, this is accumulation function, so where have we accumulated the most area? And so from here, we would have accumulated 10, but at 12 we would have gotten up to 14. So at x equals 12 is the max for that. And the absolute min is where is the least, and that's going to be at 0, actually. Because remember, as we move this way, the area is positive, or the accumulation, I should say, is positive. All right, I know this stuff is confusing. We're going to spend a couple days on it. Let me know if you have questions. Otherwise, I'll see you in the next lesson.